Any contributions? Anybody who needs a team or a group for the assignment? Or are you guys all sorted?
Seems to be fine for now, ma'am. Thank you.
Okay, then that's good. So for today's class, we are going to continue with the exercises that we started with in the last class. So I hope you've tried some of them and you understand how to work out the questions that are given there. So that is how the questions will be asked. Like I said, I get all these questions from past tests and past exam papers. So if you want to know what your test will look like, what your exam will look like, do the exercises and then you'll see what they will look like. So I think we did the first one. Let me just open this. We did the first exercise, and number 2. So we'll start with number 3. Number 3 says the amount of time that a customer spends waiting at an airport check-in counter is a random variable with a mean 8.2 minutes and a standard deviation of 1.5 minutes. Suppose that a random sample of n equals to 49 customers is observed. Find the probability that the average time waiting in line for these customers is A, less than 10 minutes. So whenever you're given a question like this, first thing you should do, write down the information that you are given. So we are told that the mean, which is mu, this is equal to 8.2 minutes. Then we are also told that the standard deviation is 1.5. So standard deviation, this is sigma. This is equal to 1.5. And then we're told that a sample of 49 customers is observed. So the sample size n is 49. So small n represents the sample and big N represents the population. So you should read the questions carefully. In the question, it might not always be that the standard deviation is given. It might be the variance that is given. So if the variance is given, all you need to do to get to this standard deviation is to take the square root of that. So read it correctly. So here everything is given for us. We don't need to work out anything to change it, like changing the variance to the standard deviation. So the first thing we're asked to do, A, is to find the probability that the sample mean, x bar. I think maybe in the last class I wrote just x, but it should be x bar because it's the sample average. This is less than 10. So this is what we are trying to work out. Okay, so here, just by reading this question, I think we're expecting this probability to be very high because we're told the average waiting time is 8.2 and the standard deviation is about 1.5 minutes. So most people should wait between 7 and 9. So if we're asking how long, what is the probability that somebody would wait less than 10 minutes, almost everybody waits less than 10 minutes. Okay, so what we need to do here is we need to standardize. So we know how to do that. This is the probability. Now when we standardize x bar, we take x bar minus mu, then we divide this by the error. This is given sigma over the square root. This is square root Okay, maybe writing too small is not good. The square root of n. So that is how we standardize. And what we do on one side of the inequality, we need to do on the other side. So with our 10, we will subtract mu. Our mu is this 8.2. So we say minus 8.2. And then we divide this by sigma. This is 1.5. Okay, what is happening with my pen now? Then we divide that by the square root of 49. So I'm sure you have calculators with you. Can we work this out and somebody tell me what we will get? So here, the first one, x bar minus mu divided by the error, sigma over the square root of n, this just gives us z. Now the reason we standardize it is so that we can read our values from the standard normal table. Okay, so this one over here, 10 minus 8.2 divided by 1.5 divided by the square root of 14. Can somebody work that out and let me know what you get?
Ma'am, I got 8.4.
You got
8.4.
8.4. Okay, so that's what I also got. So we say that this is the probability that z is less than 8.4. My pen is failing me. Okay, then what we do from here is we go to the table. Now remember what I said, you have different tables. This is one that you might get. So whatever table you get, you should be able to read it and get the information that is given to you. So this is the one that we'll be using today. So before you go to your table, you should, does somebody have a question? Okay, so before you go to your table, you should always identify the area that you are trying to work out. So if I go back over here. So I want the probability that Z is less than 8.4. So I'm going to draw a sketch of my normal distribution. So this is looks like. And then this is normally distributed. Okay. All right, now right at the center of the normal distribution is 0, and 8.4 is somewhere over there. So it is 8. Just give me a minute. Let me try and see what is happening with my screen. Okay, so we have it's supposed to be 8.4 over there. So we want this area, sorry, not that area. We want the area that is less than 8.4. So the area that we want, let me shade it, is this area over here. This is the area that we are looking for because we want all the values that are less than Z and that over there. So what we do is we go to our table. And then from, it doesn't matter what table you are given, actually, you can read this from any table. Now here, this gives us the area, but the thing with this table is that the values only go from 0 to negative 3.4. You can see here I have negative 3.4 and 0. So that means it's reading values only from 0 to negative 3.4. So if I want 8.4, what I need to do is I can hear my voice echoing. Somebody's mic not muted. Okay, thank you. Okay, so what I was saying is that this table only reads values from 0 going down, but we want a value that is greater than 0. So what we need to do is this. Yeah. Okay, so how we can use this table is we will read this table gives us values like that. Okay, so this table reads values from 0. Here's 0, and they are going in that direction. But that's not all that we want. We need this area over here as well, because this is where 8.4 is. So we know that this part is equal to 0.5 because the normal distribution is symmetric. So the total area under the curve is equal to 1. The area on the left is 0.5. The area on the right is also 0.5. So we want this area here from there to there. Are there any ideas how we can use our table to work out this area over here? So we know that we have an 8.4 here. So 4. How can we use our table to get this area when our table is clearly giving us the area over here?
-1.
Say again.
Oh, sorry. I thought I was on mute.
Anybody else? How can we work out that area? Okay, so remember our table is symmetric. So it gives us this area over here going in that direction. And because it's symmetric, if I draw a line, if I have 8.4 over here, this pen does not want to work. If I have 8.4 over here, then this area to the right of 8.4 is exactly the same as the area here on the left. And this value here will be negative 8.4. So if I want to work out this area here, all I need to do is say 0.5 minus this area over here, because the right half of my normal curve is equal to 0.5. One half is 0.5, the other half is 0.5. Together they make 1. And this area here, this small one, on the right of 8.4 is the same as the area on the left of negative 8.4. So what I will do here is I will look for the area on the left of negative 8.4, and then I will add that, I will subtract that from 0.5. That will give me this area here. and then I will add 0.5 to that, and then that will give me the area from here to there. So let me say that again. If I want to work out, I should shade them, then it's easier. Okay, and see this green area over here? So the green area is equal to 0.5 minus the unshaded area over there. Okay, and the unshaded area, I would get it from reading the table, because my table gives me values that are on the left of 0. I will read the value of negative 8.4 because it's symmetric. The area on the left of negative 8.4 is exactly the same as the area on the right of 8.4. Okay, so we go to our table, and if we look at that, our table only stops at negative 3.4. So that tells us that the area beyond negative 8.4 on the left of negative 8.4 is almost 0. Okay, so if we go back, okay, so from our table, what we have is, if we have a normal distribution like this area here, which is negative 8.4, the area over here is approximately equal to 0. So if this area over here is approximately equal to 0, it means this area over here is approximately equal to 1. So that means that the probability that Z is less than 8.4, this is approximately equal to 1. And that makes sense because we say that the waiting time is around 8.2. The standard deviation isn't that big, it's 1 minute. So most people are in that range between 8.2 and a little down. Okay, so this one here, our probability is approximately equal to 1. Sorry, 10. Why am I saying 8.4? It's 10. So the probability that the waiting time is less than 10 minutes is approximately equal to 1. So you can almost definitely say that any person waiting in that line will wait less than 10 minutes. So again, because this is a word problem, we should answer our question with a sentence. So you would say something like the probability that the average time waiting in line probability that the average time waiting in line for customers time waiting being less than 10 minutes is approximately 1, or you can say it is 100%. Okay, so that is how you would answer it. So you can word it a little bit different. I just want a sentence that says something similar to what I have said. Is that one fine?
Honestly, no.
What's the
This
problem?
the problem was getting the whole thing,
The area.
the area that got me lost so completely. And then why did we change 8.4 to 10?
I think that was the 10 was in the question. Sorry. I shouldn't have done that. I'm getting confused between my tables and my values. It should be 8.4. And in the question, when we answer it, it should be 10. Okay, so this 8.4 is fine. And this is where the 10 goes. Okay, so let's go over it again. So we standardized. Is the standardizing okay?
Sorry, ma'am, can you move the slide back to the you're working instead of the question?
Let me see. Okay, this one here.
Okay, I got it. Thank you.
Okay, let's go over it again. Okay, so we standardized it. I think the standardizing is a basic thing. So you just subtract mu, you divide by standard deviation over the square root of n. So I think that one should be fine. Now it's reading the data. I think that's reading the table that is a problem. Okay, so let's say this is your normal distribution. You know that you have 0 right there in the middle. Then we say we want the Z to be less than 8.4. So what you do on your normal table, on your normal curve, is you put the point 8.4. Now 8.4 is somewhere here because it is bigger than 0, so it's on the right of 0. So you want all the values less than 8.4. So all the values less than 8.4 are these. So this is the area that you are looking for. Okay.
Okay,
Now the
ma'am, I have a question there.
yes.
The 8.4 is referring to time, correct?
No, the 8.4 is not referring to time. The 10 is referring to time. Then we
The 10
standardize it. We
minutes.
change, yeah, we change the 10 minutes into a Z score.
Because
It's
here's
not,
my question.
yes.
Because according to the graph that we're looking at, it's 8.4. Yes, I understand that 10 refers to the minutes, and that's what we're looking at, less than 10 minutes. All right. And then the 8.4 is now the what calls the average, if I'm not mistaken. So in the event of time, in my mind, you have waiting from 8 minutes to 0 minutes. You cannot wait less than 0 minutes. It means that even before you got helped, you were already being helped. That's why my brain is stopping at 0. Like, why are we taking into consideration all the other factors below 0? Because no one can get helped already without being there. You with me?
No, I understand what you're saying, but this 8.4 over here is not time, because we changed our time. We started with our time, it was 10. We subtracted mu, and then we divided by sigma over the square root of n. It is no longer time.
Oh, okay. Yeah, you answered my own question now. Sorry.
Okay. So this is no longer time. That's why it goes from minus infinity to positive infinity. Okay. with your what is it, your mean, you'll get something like this. X is less than 2, for example. This 2, because it's referring to something physical, whether it is the number of cars or something, that one will never be below 0. Okay, then when you standardize it, because you want to read the information from the table, it can be below 0, so it's no longer time. Okay, I hope that's okay. Right, so like I was saying, we want to read this information here from our table. So we're looking for this area in green over here. Now our table gives us the area on the right. What we could get from the table is this. If we took negative 8.4 and read this area, that is what our table would give us. So what we can do is read the value for negative 8.4 and then subtract it from 1. So you can say 1 minus whatever area we get over here. This will give us this area here. And this area here is exactly equal to that area over there because of the symmetry of the normal curve. Okay, so what we do is we go to our table, and our table only stops at negative 3.4. So values smaller than smaller than negative 3.4 are approximately equal to 0. So it's almost negligible. So what that means is that this area here is approximately equal to 1. And this area, which I'm getting from my table, I'm getting it from the table in the sense that it doesn't appear on the table, which means it is approximately equal to 0. So this is approximately equal to 0. Okay, so if this is approximately equal to 0, then this small area over here is approximately equal to 0 because of the symmetry of the normal curve. Okay, and if this over here, this is what I have on my curve from the table that I am given. Yeah. Okay, that's supposed to be curve. That is approximately 1, and because of the symmetry, it is equal to this one over here. This is also approximately equal to 1. So that is why we say that the probability that the average waiting time for customers being less than 10 minutes is approximately 1, or it's 100%. So we can guarantee the customers 100% you will not wait more than 10 minutes. It will be less than 10 minutes. Okay, let's look at another one. Next one. B. B says, what is the probability that the waiting time is between 5 and 10 minutes? So again, think about the question that the waiting time, just hold on. Okay, so we are looking for the probability that the waiting time is between 5 and 10. Okay, so this is what we are looking for. Now we know that the average waiting time is around 8 minutes. The standard deviation is 1.5, 1.5 minutes. So again, when you think about it, most people are waiting between 7 and 9 minutes. So you expect a very high probability that the average, a very high probability that the waiting time is between 5 and 10. Okay, because these are very far outside of our range. Okay, just a moment. Okay, then what we need to do is we need to standardize our values. The reason we standardize them is so that we can read them from our standard normal table. So this is the probability. Then we say 5 minus mu. Mu here is 8.2. And then we divide by standard deviation. This is 1.5. And then this is divided by the square root of 49. Then when we standardize x bar over here, we will get z. And then on the right, we will do the same thing. We say 10 minus 8.2 over sigma. This is 1.5. And then we divide this by the square root of 49. So can you guys work this out? On the left of Z, what do we have? So when we say 5 minus 8.2 divided by 1.5 over the square root of 49, what do you get? Okay, anybody? What do you have? 5 minus 8.2 divided by 1.5 divided by the square root of 49. What do we have?
Negative 224 over 15.
Is a decimal? Is our,
Yes.
what do you have as a
I've
decimal?
got negative 14.93 rounded
Okay.
off.
Okay, so usually we round it off to 2 decimal places because that is the number of decimal places on our normal table. And that is also what I got, negative 14.93. Okay, and then on the right, what do we have?
8.4.
8.4. Okay, so it's the same 8.4 from the previous question because we already standardized 10. Okay, so before you go and read your table, draw a picture of what it is you want to read from the table. So this is your standard normal. This is what it looks like. 0 is always in the middle. Then you put your two endpoints. Negative 14.93 is somewhere here. So you have negative 14.93. And then 8.4 is somewhere over here. Okay. Now this one here, just by thinking about it, because our table can read only up to negative 3.4. So we are going way beyond negative 3.4. We are going to negative 14.93 and 8.4. You can just by looking at it, you can say that this area over here is almost equal to 1. Okay, So if you wanted to read this from a table, it is not difficult. We will look at some examples where we do have values that we can get on the table. But here, because we have such extremes, we can confidently say that this area over here is approximately equal to 0. And the same thing over here, this area is approximately equal to 0. So obviously this area on the left of negative 14.93 is smaller than the area on the right of 8.4. So for 8.4, we already worked it out. We said that it is approximately equal to 0. So even less than approximately equal to 0 is definitely 0. So here we can say that the probability
Ma'am,
yes.
I don't understand how the numbers beyond 8.4 are approximately equal to 0, but the ones that are between 0 and 8.4 are approximately 1.
Okay, that is because we're talking about the area of the curve. Okay, so let me just scroll down. So this is our graph here. Okay, so I know that the entire area under this graph is equal to 1. Let's say it just stopped here. This is a shape. The area of this shape is equal to 1. Okay, so that's what the shape, that is what the area under a normal curve is. That is the definition. Now, if, for example, I know the area, let's say from somewhere here, let me use a different color. Okay, let's say I know this small area over here. I hope you can see it. Okay, if I know that area over there, I can always work out the area here because I know the entire shape is equal to 1. So if I know this one here is equal to something, I will always just say 1 minus this something over here. Now, if this part here, the little yellow one, is equal to 0, then it means all the area is over there. Okay, so that it's obviously not, because you can see it's a tiny little part, but it's so small that you can say all the area is over there. So if this is approximately equal to 0, because it is so small, we can't even read it from our table. And then we have another area on the other side, this part here. It's so small, it's approximately equal to 0. It means the entire one, because we know the area under the curve must be equal to 1. And you've taken away a little small part, the yellow part, which is almost nothing. And you've taken away another small part over here, the blue one, which is almost nothing. You are left with almost everything. That is why I say this area here, the one I've not shaded, is approximately equal to 1.
Okay, I get it. Thank you.
Okay,
So basically,
yeah.
does that mean that because the table that we are working with does not have the values which we have for our probability, that we are just basically using approximates? Is that correct?
Yes, but the approximate is good because it's not. Let me see. Yes, we are approximating it because you cannot read it from the table. It is so small that you cannot get a value from the table. So if your table does not even estimate it, then you say it's 0.
Okay, so that
Yeah.
makes a lot more sense now, because now it's basically saying that basically when we get to the word problem. Okay, let's just continue and then we'll get to the word problem and then I'll add my input.
Okay. Right. So, okay. So Again, because this is a word problem, we answer with a sentence. We say the probability that the waiting time is between 5 and 10 minutes is approximately 1, or you can say it is 100%. So always try and get an intuitive understanding of what is being asked here. So again, remember the average waiting time is around 8.2 minutes. And then the standard deviation is very small. That means we don't get a lot of variability in the waiting time. Most people will wait around 8.2 minutes, okay? And 8.2 is right in that range between 5 and 10, okay? So you expect almost everybody to be included in the range of waiting 5 to 10 minutes, okay? Then C says less than 6 minutes. So C, the probability that the waiting time is less than 6 minutes. Okay, so again, this one, just by thinking about it, we say the average is around 8.2 and the variation from 8.2 is so small, we are expecting this to be very small, almost zero, okay? Because most people, almost everybody is waiting around 8 minutes. So if somebody says that they waited less than 6 minutes, that is a rare thing, okay? So again, we would standardize it. So we will say this, when I standardize X bar, I get Z. Then I say 6 minus mu. This is 8.2. Then I divide by, sorry, not that, sigma, 1.5. This 1.5 divided by the square root of 49. Okay, so again, can you guys standardize 6 and then let me know what you have?
I got minus 10.26 or
Okay.
3. Zero, I don't know.
Okay. So this is probability that Z is less than negative 10.26. Okay. So again, we leave it to 2 decimal places.
Ma'am,
Yeah.
because it's 266, 2 decimal places, so it'll be 27.
Okay, so 2627, that's fine. Please round it off correctly. If the third decimal is 5 or more, then you round the 6 up. Okay, so here you got 10.27. Okay, so again, we're trying to get an intuitive understanding. All right. So we say that we're expecting this to be very small because, again, most people wait around 8.2 minutes and there is such a small variation between the waiting times. Okay, so on our curve, this is what it will look like. Okay, so we know that 0 is right in the middle over there, and then negative 10.27 is on the left of 0, and it's pretty far from 0, so it's going to be somewhere here. So this is where negative 10.27 will be. Okay, so we're looking for this small area over there. So again, here you can see that the area is so small. Our table starts reading from somewhere here, which is the negative 3.4. Okay, and everything after the negative 0.4 is approximately equal to 0. So if you move even further, getting closer to negative infinity, that means your area is even smaller. It's getting much, much smaller. So already when you are at negative 3.4, your area is approximately equal to 0. So here at negative 10.27, this is also approximately equal to 0. So if somebody tells you that they waited less than 6 minutes, that is very rare. Okay, so it's almost impossible that anybody will wait less than 6 minutes. That's what it means. Are we fine?
Yes, ma'am.
Okay, then let's look at number 4. With number 4, we are told that the average lifetime of a light bulb is 300 hours and the standard deviation is 696 hours. A random sample of 36 bulbs is taken. What is the probability that the average lifetime of the light bulb in this sample will be equal to or greater than 3219.24? Okay, so again, always good, write down the information that you're given. So we're given this 3000, that is our average. So mu is equal to
Sorry, ma'am.
3000. Yes.
Did someone post this question already on the WhatsApp group?
This is from exercise 3 that we're doing on Monday. We just didn't finish it.
Oh, okay. Can someone share this this document again, please?
I think it's on the team's homepage as well. So if you look at the last lecture we did, maybe slightly above that or slightly below that, you should be able to see it.
Okay, thank you.
Right. Okay, so again, we write down the information that we're given. So we know that mu, the average lifetime is it is 3000. And we're told that the standard deviation, sigma, this is equal to 696 hours. And then we take a sample. How big is our sample? Our sample is 36, so n is equal to 36. So this is what we have. Okay. Then we want to work out the probability that the average x bar is equal to or greater than. So this is greater than or equal to, greater than or equal to what? 3,000. 3,219.24. Okay, so that's what it looks like. Okay, so again, first thing we need to do, we need to standardize our x bar. So to standardize, we will subtract mu, and then we will divide by sigma over the square root of the sample size. So when we do that, we'll have P, and then when we standardize x bar, we get Z, and we say that Z is greater than or equal to, we'll say 3 219.24. The point is over there. And then we subtract the mean, which is 3,000, that is given to us. This is all divided by sigma, which is 696, divided by the square root of n, which is 36. So can you standardize the 3219.24 and let me know what the Z value will be?
I got 19.06.
19 points. I don't think that's right.
I got
It's
1.89.
1.9.
Okay, we want 2 decimal places, remember? So always have 2 decimal places. So instead of 1.9, it's 1.89. Okay, so that's good. Okay, so when we've standardized it, we get P is greater than, sorry, Z is greater than or equal to 1.89. So again, before we go to our table, now 1.89, remember our table, we can read values between minus 3.4 and positive 3.4, and 1.89 is in that range. So we're not going to get something approximately equal to 0. Okay, so you draw a representation of what it is we're looking for. We say that 0 is always in the center, and then 1.8 is somewhere here. So this is like our cutoff area, but we want the area that is greater than 1.89. So greater than 1.89 means we want this area over here. Okay. So we need to figure out how we are going to read this from our table. Now this here is 1.89. Now what we can do from our table, which we will see now, is we can read the area like that. Here I have negative 1.89. I can read this area from my table, and because the normal curve is symmetric, this area, it doesn't look like they're the same just because of the way I'm drawing it. It's a little difficult to draw them, but these two areas are the same. Okay, so just think of it as if the curve has been flipped around. Okay, so if we get the area that is below negative 1.89, that is the probability that Z is greater than 1.89. So we go to the table in order to get that. So here is our table. So what we do is, this is our Z.
Cutting.
Am I cutting? Can you hear me now?
We can hear you now. Yes, ma'am.
Okay, can you see my table?
Yes, ma'am. Yes.
Okay, so to read the table we have, and can you see my cursor moving?
Yes, ma'am.
Okay, so this column here gives you the Z values. So this, you'd go to, we're looking for 1.89. So on the Z score, you will look for negative 1.8. The reason I'm looking for negative 1.89 on the table is because that is the only value that this table gives us. Okay, so it doesn't give us a positive 8.9, so it stops at 0. We have another table. Okay, for the next question we can use a different table. I see I have another one over here. Okay, but the point is you should be comfortable using whatever table you are given. So I go over here, I look for negative 1.8, there it is. Now these numbers here, 0.00, 0.01, this are the second decimal after the first decimal. So here, my first decimal is 8. Then if I read from the first column, the second column rather, this will be 8, 0. Then that will give me 8, 1, 8, 2, 8, 3, 8, 4, and so on up until 8, 9. So the value we're looking for is negative 1.89. So this is negative 1.80, negative 1.81, negative 1.82, and the one we're looking for is right at the end over there. So what we should get is 0.0294. So here you can see there's a point. It means there's a 0 in front of that. So the probability that Z is greater than or equal to 1.89, this is equal to 0.0294. So this is how it was written on my table, but there was a point before the 0, so I need to put a 0 before the decimal. Okay, so is that fine on reading the table? This is a 4.
Yes, ma'am.
Okay, then again, because this was a word problem, your answer should also be in words. So you can say something like the probability that the average lifespan of the light bulbs in the sample being greater than or equal to 3219.24 is 0.0294, or this is also equal to 2.94%. So to get a percent from here, I just multiply it by 100. Okay, so you can write a sentence, the probability my pen is not willing. Okay. Average lifespan is greater than or equal to, and then here you write the original X bar that you were given. So I'm not going to write 1.89. I say 3219.24 is 2.94%. Or I could, there's a percent over there I'm trying to fit in. It just does not want to go through, but there's a percent there. Okay, so that is how you would answer it. Okay, so and this does make sense because we are told that the average is around 3,000, and we want to work out what the probability of getting a sample whose average is greater than 3,200. Okay, the 3,200 is within the range when you consider the standard deviation, because the standard deviation is 696, but greater than that, now we're going to like 4,000 hours when our mean, our average is around 3,000. So we're not expecting a very high value for that. Okay, then number 5, if that is fine.
Ma'am?
Yes.
Ma'am, sorry, would you please repeat this question again? I missed something somewhere, please.
The question says the average lifetime of a light bulb is 3,000 hours with a standard deviation of 696 hours. A random sample of 36 is taken. What is the probability that the average lifetime of the light bulbs in this sample will be equal to or greater than 3,219.24 hours?
Sorry, I meant the answer. Sorry.
Answer.
Yeah.
This one here, the probability.
Just before the area under the graph. Just
Which part here?
when we're standardizing it.
Okay, want to standardize it. Let's see. Let's see. Okay. Okay, this is where we're standardizing it. Okay. Did you have a specific question or you just wanted to see it?
No, I just wanted to see. Thank you.
All right. So then move on to the next question, number 5. Number 5 is similar to number 4, except there is the B part of number 5. So the A part of number 5 is exactly the same as what we did in number 4. Then 5B says, what is the probability that the average lifetime in the sample will be between 2,670.56 and 2,809.76. Okay, so again here, before you answer the question, you should try and think, what do I think this probability is? Am I expecting something high or am I expecting something low? So let me write that down for you guys who don't have the question. So essentially what it is saying is, what is the probability that the lifetime of the bulbs is between 2670.56 and 2809.76. Okay, so we know the average is 3,000. And you've taken a sample, you want to work out what is the probability that the average of this sample is between 2670 and 2809. Okay, so here when I just think about it, I'm expecting this to be low. Okay, it shouldn't be too high because my average for the population is around 3,000 and the standard deviation is around 69 or close to 700. So it shouldn't be too low as well. So you're maybe like a medium. So it's just thinking about it. Then when you get an answer, you're able to tell, does my answer really make sense or does it go along with what I was thinking? So to do this one, we do the same thing, we standardize. So let's say this is the probability that 2670.56, we subtract our mean, which is 3,000. Then we divide by sigma, which is 696. And then this is divided by the square root of 36. That is a 36. Okay, when we standardize x bar, we get z. So this is z. And then we do the same thing on the right. We have 2809.76. Then we minus 3000. Okay, we can finish that. It's minus 3000. Then we divide by 696 over the square root of 36. Okay, so can you standardize this? You should also close your bracket. And remember, this is a 3000, not just a 3. My pen can just is refusing to write over there. So when we standardize the one on the left, can you tell me what you get?
I got negative 2.89.
2.89, is that right?
On
Negative 2.84.
8. Why is it 84?
Negative 2.84.
Did anybody else get something different?
Negative 2.95.
Negative 2.95. Okay, I got negative 2.84. Okay, so just go over your calculations, see if you missed something. It might help to also do this in steps, work out the numerator, and then work out the denominator, and then do the division. That might be better. Otherwise, when you type it in on your calculator, you need to put brackets. So they need to be brackets here and put brackets over there. And then the fraction part is just a division. Okay, so I got negative 2.84. Okay, and then when we standardize the one on the right, can somebody tell me what they got?
Negative 1.64.
Okay, negative 1.64. Did anybody else get something different? Okay, I also got negative 1.64. Okay, so this is the area that we're looking for. We're looking for the area between the Z values negative 2.84 and that's a 2 and negative 1.64. So again, what you should do is draw a sketch and try and identify.
Ma'am,
Yes. Yes.
I don't know why I got negative 1.70 or like 706, not 1.64. I put the brackets and all of that.
Did you subtract 3,000 or 3 here? It's 3,000.
3,000.
Okay. That's what I got. 2809.7 minus 3,000 divided by 696 divided by the square root of 36. Okay, I'm still getting negative 1.64.
Are you computing all of the digits in one go, or are you, like ma'am said, are you taking it piece by piece? Because I took it piece by piece and I got negative 1.64.
Okay, I'll take it piece by piece and then I'll see if I still get the same answer as you guys.
Okay. Right, then this is what we have. So we say we need to draw a sketch and try and figure out what area we're looking for. So this is what we have. So 0 is always in the middle. Then we have negative 2.84. That will be somewhere here. And then we have negative 1.6. That is somewhere over there. So we're looking for this area over here. Okay, so like I said, I want us to use slightly different normal table. So this is the one we've been using. And this is another one that you could get. Okay, so they will give you the same information. It's just that they're reading them differently. So here, this will go all the way from, it starts from 0. It goes to 3.4. So it's almost like the reverse of the other one in a way. Okay, so if we want to read this one here, and this is the area that we are looking for. So this is negative 2.84. This is negative 1.64. Okay, so try and think about what you're looking for depending on what you are given or what table you are given. So if you look at this table, it's reading from 0 to the positive values, because here at 0 over here, it says that the area from 0 going on is 0.5. And then as you go down, your area is decreasing. Okay. So let's go back here. Now we need to figure out a way to read this part of the table, given the table that we have. Okay, so what we can do is we can read the area from 0 to 1.64, and then the area from 0, so we can read this area here. And then we can also read this area here. So reading the negative and the positive ones will give us exactly the same values because our table is symmetric. So remember that our table is symmetric. So whether I say negative, read the negative or the positive ones, the values will be the same. Maybe on different sides of the numbers, but the value itself is the same. Okay, so what we could do is we could read the area from negative 1.64, but our table is giving us this area here. Sorry, I'm trying to find my eraser. So from our table, what it is giving us is this. So if I read the area from 1.64, it'll be this area going that way. Then the area from negative 2.84 is this one going that way. And this is the area that I want. So I should just say this one minus whatever I get over here. Does that make sense?
Yes, ma'am.
Okay, so what we do is we go to our table now. And then we look for 1.64. Okay, so remember you start in this column over here. So 1.6 is over here, then 1.60, 1, 2, 3, 4. That is what we will have. So it'll be 0.9495. Okay, let me write that down. So this area here, the probability that is negative 2.84 Z negative 1.64. We say this is 0.9494, and then we are going to subtract the smaller area. So we go back to our table. We look for 2.84. So again, we start in the Z column. So 2.8 is over here. So if 2.80, okay, I'm not reading this correctly. 1, 2, 3, 4. So here I'm getting 0.9977. So it's subtract the bigger one from the smaller one, not the way I've done it here. Subtract the smaller one from the bigger one. Okay. So this, write the bigger one first. 0.9977 minus 0.9494. Okay, then this you just do on your calculator. And I got 0.0482. 0.0482, which is about 4.82%. Okay, then what you do is you write a sentence to answer the question. So you can say the probability that the average lifetime of the bulbs is between 267, 0.56 and 2809 is 4.82%. So that's how you would do it. Okay, do we have any questions? I see it's already 8 o'clock.
No, ma'am. It's clear.
All right, so there's still questions 6 and 7. Please try that one. Remember the assignment. I hope everybody has a group. If not, please use the WhatsApp group to see if there are groups that are not full that you can join. Do not wait until the day before the assignment is due to say that you don't have a group. Nobody will let you because they've done all the work. Okay, so have a good evening. Just practice some of the questions. There's lots of resources online, and I will see you guys on Monday. Have a good evening.
Thank you, ma'am. Have a good evening.
Thank you.
Thank you. Good night.
Night.